very good self-promoter. I promote other people pretty well. But anyway, I put together some a little bit. I started this research over the summer, and and then I got a gig working for somebody that was working for Singularity Net, and I slacked off on this again. But so I picked it up in the last month or two and tried to finish it. But basically, this picture here is inspired by Hot Shots Part Deux, which is a pretty funny comedy. Anyway, yeah, when I started the Northwest AGI Forum, I kind of had three goals that I knew I wanted to cover. An investigation of understanding, an investigation of reasoning and judging. And we've done a lot of other things, but we've also covered understanding, and all of these events, all the prior events are in the archive. The group itself is now about 5 or 6 years old. But I mean, so take understanding, reasoning, and judging. They kind of compose thinking. So that's why I wanted to cover all three of those. But for like an understanding, we kind of came to the conclusion that most people think there's levels of understanding. You've got a basic understanding. You've got more understanding of causality and things like that. You build up intermodal, and then there's a lot of I got to keep admitting people here. And then hi Brett. And then we went through judging and looked at kind of a pretty wide this psychological and philosophical origins of judging, and the mind being kind of a measuring instrument. And ultimately kind of I arrived at what a true judgment was, which is kind of characterized by having lots of unknowns. And then so that left reasoning. And then last summer I did some research on reasoning, just from the standpoint of not from a computer science standpoint, but here just is a really basic review that so basically I looked at reasoning and rationality, and they're both kind of interconnected, but they're distinct too in a way. And reasoning, this is the starter definition I got from the Dictionary of Philosophy. I've got the links here anyway, but reasoning is the process of inference. It's the process of passing from certain propositions already known or assumed to be true to another truth distinct from them but following from them. It might not be something altogether new. It might just be an illumination of what the facts are and the situation is. But basically, it's this process of you're starting with, some situation and some set of facts, and you proceed to something that's new. That's core to reasoning, and it's usually, a conscious process. And rationality is more like how you do that. By what strategy? Are you looking out for your own self-interest? Are you being coherent in the way you approach reasoning? So reasoning and rationality, just from like I went back and I looked at the Greeks, and the Greeks thought that the nous, that there was this prime source of everything, and that created the nous. The nous, N-O-U-S, was the source of reasoning. But today we're going to turn to how reasoning has emerged in artificial intelligence. And so even prior to the advent of term AI having been coined, they were already working on, a group was already working on what they were calling automated reasoning. And that was pretty famous names by now, Newell, Sean Simon. And all they did was basically invent good old-fashioned AI with the symbolic search trees, heuristics, list processing, a language called IPL, which I think is kind of similar to LISP, which is a lot of parentheses. This is all symbolic, basically, at that point. And then, so on this original team that created this, quote, first AI program, they only Shah had some kind of programming experiences. So programming experience. So Newell and Simon didn't. So whenever I read this, I think of all those job ads where they ask for 2 years of experience with it. And here these guys just invented old symbolic AI, and with only one guy that could ever had done any programming. So they followed. They apparently they were not a hit at the Dartmouth conference for some reason, which I thought was kind of an interesting side note to this thing. Simon just saying they didn't want to hear from us. There must be some more to it than that, but anyway, it wasn't very popular. General problem solver is one of those, really first, great AI efforts, and this was a means of getting from a start state to the end state with basically a means-end analysis, I think. And I don't know that much about it, but it was kind of one of the first efforts that exposed in reasoning, you get the combinatorial explosion, that there's just so many things that can happen and you can't pre-program for everything. Now I'm going to talk about traditional AI reasoning for a little bit, and basically, as a lot of this is review. Most of you know a lot of this already, but I mean, typically the way it used to be done, like I'm going to say the 20th century. So definitely prior to deep learning, it was mostly symbolic, and then you'd start off with you'd kind of pick one of the reasoning methods you wanted. Deduction, there's deductive reasoning, there's inductive reasoning, abductive. There's a list here. Common sense reasoning, fuzzy reasoning, there's modal logic, case-based. So the way things were done then, and there's different ways of organizing this, but the way things were done then is that you kind of would start off with a problem that you wanted to solve, and then based upon what problem you wanted to solve, then you go and pick one of these reasoning methods. Like you might just need deduction. You don't need to learn anything. First, you can just write all the rules beforehand. So this era was kind of characterized by discrete types of reasoning, and you'd start off with your problem and then come up with your decide what reasoning technique you want to use. But they didn't. They were typically kind of brittle and usually symbolic, and usually you'd see the inference engine was the kind of the center of all the focus here. And I've just got some examples. Most people have heard of all these famous examples, except for mine at the end. But Myson was deduction, and strictly deduction and backward chaining, meaning you started at kind of backward chaining is you start kind of at your goal, and then you try to justify what the goal by chaining backwards. Could diagnose bacterial infections. Inductive logic programming was 35-year-old now effort in symbolic learning, induction, and basically you'd input positive and negative examples and then output basically prologue looking rules. So it could basically learn, but keep in mind, the way things worked in those days is that it was tough to integrate learning and deduction. I mean, induction and deduction. Well, it still is basically, but and then another one a lot of people have heard of, psych, was an attempt to, a grandiose attempt to codify all the common sense reasoning rules that you need to actually, do some thinking. And I think most people regard this effort as possibly a partial success or partial failure, however you want to look at it. But it really exposed the limitations, as a lot of people know, of symbolic brittleness. Not very fuzzy, doesn't yield well to, okay, it's a kind of this. And then I put my own scale suggester system. Let me see, I've got somebody trying to admit here. Okay, never mind. Disregard that comment. So 25 years ago, I was trying to learn the CLIPS language, and I wanted to use a application domain I was familiar with. I picked jazz improvisation. I wound up just kind of experimenting around, and I wrote a expert system basically. And you know, the way these things basically work is that you codify a bunch of rules, and then then you've got your static rule base. Somebody puts in some input, and then various rules fire. So you know, it was just typified that era. And I'm going to shift now to reasoning and cognitive architectures. So one of the main emphasis on cognitive architectures, the reason I bring it up is that reasoning and cognitive architectures, it's supposed to be more like the way, it was supposed to be more like the way we think. And then typically you can kind of, from that, you think, well, if it's reasoning the way we think, then it should be more generalized, more able to do multiple different kinds of reasoning. It may not be just stuck in you know, one particular paradigm. And it's also important to note that cognitive architectures didn't really concentrate on pure theoretical reasoning in terms of axioms like universal truths. Cognitive architectures concentrated more on, well, what's practical to get the job at hand done. We're not necessarily trying to learn any permanent invariant truths. We just want to get, you know, some problem solved. So there was an emphasis on practical reasoning. Some of the canonical famous cognitive architectures, ACT-R, SOAR is probably the most famous. Dual and Clarion. Dual I hadn't heard of before, being one of the early efforts at linking symbolic and neural AI. Clarion, the same thing. But mostly these ancient now seeming cognitive architectures were based upon symbolic processing and people thinking out a structure and a procedure in advance. And this depiction here is the so-called standard model of cognitive architectures, in which there was an effort to make a kind of a generic model of a cognitive architecture in the same fashion that there's a kind of a standard model of physics. That was kind of the inspiration of it. But the inventors of the so-called standard model, which I think was led by John Laird, they looked at you know, like there's hundreds of cognitive architectures. They looked at a lot, and then they tried to distill and create the common denominator for all of them. And this is what they came up with. These two depictions, the upper and the lower, they're both depicting the same thing. And they essentially, what happens is a perception might come in, and then based upon some perception, the central executive of the cognitive architecture might look into procedural long-term memory. And procedural long-term memory would probably have some kind of a reasoning scheme that would be applicable to the problem at hand. And then perhaps it goes around the cognitive architecture, chugs through a few more cycles. It does a lookup into a long-term memory. Oh, it reminds me of some episode. Declarative long-term memory typically being composed of prior episodes and semantic knowledge. Semantic being things like a dog is a mammal, and these kinds of truths that we usually take to be implicit. So, I mean, the reason I bring up this standard model is that basically there's a lot of reasoning going on in here, and the procedural long-term memory being kind of like a Lang chain in a way, is now we're gonna do this, and then we're gonna do that, and then we're gonna do that, and then we're gonna come to our conclusion, things like that. So there's the standard model. And one of the so SOAR was probably the most famous cognitive architecture example around, I suppose, and it's purely symbolic. And basically, there's the way this works. It's the basic decision cycle. It seems to be fairly simple and straightforward. And really, what they mean by there's reasoning that's going on in here. So some input comes in to the SOAR cognitive architecture, and then a numerous different rules and proposals, they're called here. There's an elaboration process that goes on. Reasoning things like, if I see this, then I do that. If this happens, then I do that. Old school AI where we encode the rules. The sort could also learn, but then based upon which rule, and I don't know exactly how to explain this because I'm not really an expert at SOAR, is most appropriate. One of the rules, or maybe it might be a set, fires. There's an application. This is a closed loop, and it goes around in a circle. So the point is, it tends to be, this reasoning is more like the way a human would think than the kind of standalone reasoning architectures that I talked about earlier. Now I want to talk about NARS. NARS is a general. Say Pei Wang started working on this, I believe, in the 90s, but I didn't really hear about it until like around 2000, 2002, when the AGI movement really, I first started to notice that, and it was Ben Goertzel mainly, and Peter Voss and Pei Wang, and Pei Wang, and I got an email from him like around 2002. Anyway, but Pei Wang was working on this, and he wanted to make it more general, and again the emphasis is on non-axiomatic. So he didn't want to make something where it would learn some kind of universal truth. It had to be adapted to the situation at hand, and nothing in NARS is ever perfectly true. I don't know if you can get to 100% true. It just takes truths in degrees, and it adds up the number of times it sees some kind of something happening, and then it based upon that, it does what it thinks is the most practical thing. But I'm going to go to the next screen grab, which is kind of a lot, and don't try to read all this right now if you don't, unless you really want to read it. But the point of this is that you see on the left hand side it says now NARS axiomatic language 1, and then it goes all the way up to 9. And what he did, this is the point of this slide, is that what Pei Wang did is he started out with term logic, with Aristotelian logic, and as he said here, he added in some things from inductive logic, probabilistic logic, fuzzy logic, relevance logic, non-monotonic logic. So he put that in the lowest level. He moved up kind of a hierarchy here, and he added set logic, set theory. And then on top of that, layers 5 and 6, propositional and predicate logic. And then until finally more emphasis on logic programming. So the point I'm trying to make here is that he's trying to incorporate multiple different types of logic, different reason. So multiple different types of reasoning. Remember when we started off, I emphasized that, good old fashioned AI, you'd use this reasoning technique, you'd use that reasoning technique. You'd have to pick the kind of reasoning that was relevant to the problem at hand. But here Pei Wang is trying to, generalize this, to try to say, well, look, we're going to put all these different kinds of logic together. So this is an effort at general reasoning. Before I move on to the next one, I think Ben Goertzel's approaches usually seem to remind me of the same kind of thing in a way, because in Ben Goertzel's approaches, and I've been watching these for a long time, he usually has some kind of central memory kind of structure, which has concepts, things that happen, what he calls atoms. So like an atomic thought, and how these can build up and create, to be used in the process of a judgment. But the point is that he's got this central knowledge store, but around the periphery, he builds independent, discrete reasoning methods. Like he's got probability and other inference engines and such. But again, so these earlier AGI techniques were designed to build in more than one reasoning method. It wasn't just one reasoning method. And Michael Miller, who tells me he's going to show up pretty soon, has also been working on his premise system. And in his scenario, he's got what he calls the totality. And then that's, again, kind of the data and knowledge. And then he's got the reasoning agents built up around that. All of these are really symbolic. There are attempts made in all of these to build in neural networks, but cognitive architectures on the whole are basically symbolic oriented. Okay, now I'm going to move to foundation models. And here, so by the time I get to foundation models, large language models, call them what you will, there's a intentional movement away from trying to have a human really devise some kind of cognitive architecture, some kind of structure. It's a lot more, as you know, neural network. Just give me a lot of data. Give me a lot of data and examples, and we'll learn from that. And at the same time, the definitions are not very well refined either. Like here, they just say Llama, which is the Meta Facebook project. We define reasoning as the ability to perform multi-step computations and arrive at the answer. So I like that. Okay, that's pretty good. It's nice and simple. And if it works, that's fine. I got some papers I reviewed for the state of the art, or at least it was. And I've got a little bit of analysis of closed models, some of the open source models, DeepSeek, the Chinese model, and some future direction. Now, here on this, if you click on this link in yellow, there's a quite exhaustive list of different pretty contemporary models that this is a Chinese effort, and the Chinese really mean business when it comes to AI. And they've kind of got everything categorized by language, vision, multimodal. So you can look up the different. They concentrate on the open model. So there's usually papers involved with each of these. I'm going to go to the next slide. It is. I think they're keeping this mainly up to date, but of course it's hard to stay up to date. It's a lot harder than it used to be to stay up to date. But essentially, they break things down kind of in a manner reminiscent of the good old-fashioned AI, where it's still broken down into mathematical reasoning, for example, logical reasoning, causal reasoning, visual reasoning. Their taxonomy is to me, it's not completely perfect, but it gets you pretty close. So, like in this circle depiction here on the outer periphery, they kind of have the applications that these different types of reasoning can be used for. But I think it's pretty evident that we're kind of converging, instead of having individual models for different types of reasoning. We're kind of converging on hopefully a single type of model that can do all of these concurrently. I mean, that's kind of the way we think anyway. But it's pretty hit and miss, and there's a lot of work left to be done. The other paper I had was by Plaat, and it's called "Reasoning with Large Language Models: A Survey." And basically, if you've heard of, most people have heard of System 1 and System 2 thinking. That's basically Kahneman's theory. That System 1 thinking being basically you don't really have to do a lot of thinking. It's just mostly instinctual, perhaps subconscious. You're faced with some situation, you just know what to do. System 2 thinking is when you have to sit there and go, well, we've got some kind of situation. I'm not exactly sure what to do. I have to sit back and think about it. And basically what they're kind of presenting and describing in this paper was that, and this is a year old, basically that characterizing large language models as System 1, you give them the prompt, it comes up with the answer. It's not doing a lot of background reasoning. That, from the outset of ChatGPT, that was basically the way things were done. But with the advent of chain of thought reasoning, things have changed, and reasoning has kind of had a renaissance, it looks like. But so basically, what they do is they argue in favor of, or they present a kind of a theory of system 2 reasoning, aka chain of thought reasoning, where the large language model has to kind of go through its steps of reasoning, try to find errors and things like that. They present what they call a simple taxonomy. The general sequence for system 2 reasoning, large language models: generate some reasoning steps, evaluate each step, and control the execution of the reasoning. So, and they list some different methods of generating steps. You might handcraft a step yourself, handcraft a step yourself. You might have the machine, an external model, an external LLM, generate a prompt. Some mixture of that. There's so once you've got your steps generated, then you have to evaluate the result of the steps. And then again, you can a lot of tricks that they use now are to use an external model to evaluate what the first model is doing. And there's all kinds of variations of this, but the basic idea is that you're going to do some system 2 reasoning, generate the steps, evaluate the steps, and then you have to control the execution of the reasoning. And they're borrowing some cues from old-fashioned AI. So you might have to the large language model might be designed to do a kind of a good old-fashioned AI search. I mean, good old-fashioned AI's inference engine was all based upon how do you make the search efficient. So I mean, it's no different with this. There's a lot of different avenues to explore, and they also include reinforcement learning. So that's part of the control mechanism. Anyway, now I'm going to move to the contemporary reasoning models. And so OpenAI, as you know, is closed AI. And basically, when they came out with the 01 model, which I think was in the fall, they say that, well, you're not going to have to explain. Because I think people were mostly saying, well, explain your reasoning step by step. And that was the way to get large language models to act like system 2 deliberating reasoning. But so here they say you don't have to explain it. The model does not need you to say you have to explain your reasoning and things like that. They tout it as doing the thinking automatically, and they do say thinking. And it says they say that it can try different strategies and these models can recognize their mistakes. And on here I've got this amounts to the documentation for the OpenAI reasoning method that I could come up with, it being closed. So the basic idea is that you kind of start off with input, an input prompt, and then it goes through steps. They're calling turn 1, turn 2, and turn 3. So they take the input prompt, and then they add what, here you can see there's a reasoning little box here. They add some special reasoning tokens, which they don't really describe. The result of the first reasoning step takes the input that you input, and then the output, and that's the input to the next step. And then the next step creates some more reasoning tokens, creates some more output, and then the input and the output are again fed into the next step. So that's their thinking, and they are calling that thinking, that process. And here I've just got a little example where I asked it to explain diffusion transformers, and you can see it lists its thinking, its steps. I'm considering if the query pertains to such and such. I'm going to combine the strengths. That's my next step. I'm going to map, etc., etc. And then it finally will come up with the answer, which is diffusion transformers typically refer to generative models, blah, blah, blah. So it did this thinking, and then it came up with its answer. All right. And then I looked at Google Gemini Flash Thinking. They tout this as multimodal and agentic. Flash Thinking, I don't think means anything in particular. It's just marketing. And it's not a particular technique that I could see. Closed source, since it's Google. And again, they describe each step, if you will, as thoughts. And so I've been having power steering noise come out of my power steering pump. So that problem came to mind. And then so I asked it, how do you fix a noisy power steering pump? And then it said, deconstruct the problem, brainstorm possible causes. These are the steps it's taking, it's reasoning. And then eventually it comes up with, this looks like the ladder. This is just a screen grab. It said, eventually it comes up and it says, well, self-correcting. I might have said flush the fluid, but realizing there are multiple flush methods, blah, blah, blah. It refined and corrected what it had said. So it went back and it self-corrected. It didn't just dump out the usual large language model output. So there you have it with the closed models. I looked at Meta, Facebook, the Llama model, and basically, since it's open source, you get the papers, etc. And really, what it comes down to is that for large models, there's typically the first main step is creating the base model, but the base model is too crude. Really, here's Michael Miller. The base model is usually too crude to just release as a working model, so it takes fine tuning. So Meta describes some of their fine tuning steps and the problems that they ran into, and so forth. And they typically, for their fine tuning steps, they use a reward and supervised fine tuning. Supervised learning meaning it's the model is given instances where it's got some problem at hand and what the correct answer is, and then it goes through all of those. But there's also some rewards, some reinforcement that go on with that. And on the next slide, they listed some of the problems that they had in doing the fine tuning step, and then what their solutions were. And you can read through these if you want, or refer to their paper. It's things like what if you just don't have enough of the correct prompts? What do you do? And they've got a solution for that. If the reasoning trace, they go back and they look at the reasoning. How did that work? If there was a problem with that, they can correct that. They generate code and stuff like that. So they tell you what their strategies are. Now, DeepSeek is the one that everybody's been talking about in the last month or so. The Chinese large model, and typically, in all of the actually in all of the literature I looked at, they usually associate math with reasoning. So the central focus in reasoning is usually math, and so that one of the forget what the benchmark that they usually use. It starts with G, but with math, there's a lot of emphasis on that. And well, somebody pointed out, I forget where I got this quote, that TechCrunch said that the deep think, deep, also called deep think R1, DeepSeek. Anyway, people are still using deep for everything. It has to embody core socialist values. So, if you're using that, that's what it's going to have to respond in that fashion. The main point I want to make with DeepSeek is that it's they boast in their write-ups that it's using reinforcement learning exclusively. It's so remember I said before, Meta in their Llama model, they were using supervised learning. Now for DeepSeek, they're using they say only reinforcement learning. So okay, and here I got another example where explain why it's better to exercise daily than once a week. And then it went through its reasoning steps. Well, let's see. I'm going to think about the daily. Maybe consistency is a factor. And so it goes through its thinking, as they call it, and then you get the answer. And so it used its prior thinking steps. And I didn't research exactly what they're doing. It is open source, so you can find out. But here they give you the answer, which is separate from the preceding thinking. Okay, and okay, I'm just about done with my presentation. One trend I think that seems to be cropping up that's important is it's like any kind of AI, reducing the search tree. So if you ask the reasoning model what 1 + 1 is, there's really no deep thinking you have to do. You just come out with 2. So there's strategies to basically trim the search tree. And this brings me to my last slide, which is I tried to look at what the long-term trends are, where this thing is going, and I think it's pretty clear that we're going from discrete reasoning methods and techniques to probably a more centralized model, which can do all of these different techniques concurrently. It's hard really to talk about AI. I mean, you can't really have deduction unless you have common sense. They're so intrinsically combined, and so that, I mean, heading towards a convergence of models. And I think it's pretty clear that there's less human designs that go into making like sophisticated cognitive architectures. That's the trend. I'm not saying that cognitive architectures won't make a big comeback. Maybe they will, but anyway, the trend is not towards cognitive architectures and symbols. It's to the transformer and different types of learning mechanisms. And thinking is basically like Kahneman's system 2 thinking. So to me, like I said at the beginning of my presentation, thinking I kind of associate with understanding, reasoning, and judging. And if you look at these these examples that I came up with, I mean, can we say that this like the DeepSeek model is doing concurrent understanding, reasoning, and judging? They say it's thinking, but I mean, that is another trend, I think, now in that there's less analysis in terms of the fine details of what is reasoning, what is thinking. They don't really care as long as it comes up with a convincing answer. That concludes my presentation. Thanks to everybody that made it through to the end. I'm going to stop sharing.